what we are trying to do. So this is our theorem. If f is a non-singular projective surface over complex numbers and analyzed as a canonical bundle, the nested Hilbert scheme for some r bigger than equal to 2, tuple of integers, and r minus 1 sequence of effective Kerr classes, this is space we can construct a virtual cycle for, and this is that virtual cycle. It sits inside some degree of the Chaff homology of the nested Hilbert scheme, and this is the formula for the expected dimension of nested Hilbert scheme. So you can use Groth and the Riemann-Roch theorem to calculate this formula. Now, if there is no Kerr class, of course you can have nesting of points inside each other, then this whole sum goes away. You see, this depends on data I. So let me just write this one in here because this is kind of itself important. If there is no Kerr class, so if the data is equal to 0. Yeah, equal to 0. So this is the virtual cycle, and well, to construct this virtual cycle, you need some objects which understand deformations and obstructions, and I will not talk about it. Okay. So one of the things we can do is to simplify the problem and look at only n equals to 2. So two-fold nesting. This is the example in my picture. We need n1, n2, and one Kerr class for understanding the two-fold nesting of one-dimensional subschemes of an algebraic surface inside surface. So this is the theorem that he proved. The virtual fundamental class in this case recovers some of his own theories. And so this object actually depends on n1, n2, and beta. So if you set them equal to 0, in some sense if you turn them off and turn some of them on, you recover some of the own theories from the past. For example, we can prove that if the Kerr class is equal to beta, and n1 is equal to n2 equal to n, well, what is this moduli state? This is the moduli state. If n1 is equal to n2, beta is equal to 0, your map C is from ideal shape of bunch of points to ideal shape of bunch of points, and this is identity. And so it's just Hilbert scheme of points, and if you look at my formula for the virtual expected dimension, it's 2n. So here you can see that the Hilbert scheme of points, as I mentioned earlier, is 2n dimensional. The fundamental cycle sits in 2n degree of the homology, and the virtual fundamental cycle also matches with the fundamental cycle. So good. We were happy to see this. Now, if beta is equal to 0, and n2 is equal to 0, okay. If that's the case, if beta is equal to 0, n2 is equal to 0, so this is space satisfied that n1 is not equal to 0. So some ideal shape of n1 many points, n1 times point, goes to ideal shape of no points. So what's the ideal shape of no points on the surface? It's the shape of holomorphic functions. We call it O, or the structure sheet. So this is that, but every ideal shape of course injects inside O. So of course intuitively it can be seen that the nested Hilbert scheme again is the Hilbert scheme of points on that surface. However, this is important because if you look at my formula, n2 is equal to 0 now, and the virtual dimension of the moduli space is half the dimension of the actual space. And this is one of those examples where you would have a smooth space and you put different obstruction theories on it, and virtual dimension and the virtual fundamental class depends on the obstruction space, obstruction theory. So you can see in here that virtual cycle is not the fundamental cycle, it sits in half that degree. And okay, so this 2n homology class, 2n dimensional homology class caps with some n cohomology class. And that's a topological vector bundle with random using tangent. Okay. So if you put beta equal to 0, and n1 and n2 are not equal to each other by different by 1. So you are looking at nesting of points inside on this algebraic surface such that the number of points is different by 1. So this is the only example of nested Hilbert scheme of points which existed before our work. And this space is smooth actually. And its invariance as well as its virtual fundamental class were studied by Manfred Lenz, whose picture I showed, and in the paper on topological sheaves over Hilbert scheme of points in 1999. And our nested Hilbert scheme of obstruction theory and virtual fundamental class precisely captures his class. You see, the reason I'm mentioning these things is because it's not obvious that our virtual class matches this. This is actually good luck, because I could have chosen different obstruction theory and virtual class of mine which is different from his. Both of them are correct, but we were happy to see that this is the case as well. And so our invariants are exactly invariants that I calculate. If you put both of the points equal to 0, so no points, but this is just an ideal sheaf of curves. In that case, the Hilbert scheme becomes Hilbert scheme of divisors, and you can see that the virtual fundamental class coincides with the virtual cycle constructed by these three people, Zior, Kavanagh, and Okudek, and they calculated the invariance against this class, and they called them Poisson invariants. So our virtual theory recovers Poisson invariance too. Okay? And finally, if n1 is equal to 0, and beta is not equal to 0, so I1 was supposed to go to I2 twisted by some first class. I1 is the ideal sheaf of no points. So this O, and that's it. So this one is ideal sheaf of n2 many points twisted by some line bundle. If this part wasn't there, if n2 was equal to 0, if you look at this section, the 0 locus of this section gives you the divisor C, and that's the natural Hilbert scheme of divisor on that surface. The parameterizing space is just natural Hilbert scheme of divisor on that surface. However, because now you can see that your functions are having normorphic poles along the curve, but then there's a bunch of points, the picture that you need to have in mind about this is your space is parameterizing divisors with points on them. So for every fixed curve class, your space is Hilbert scheme of points on that curve. And as you vary the curve, okay, so there is a Hilbert scheme of curves that have the universal family if you like, and as you vary the curve for every single element of that invertible curve, you get an invertible point on those. So this is something which is a relative invertible point on some universal curve given by this invertible curve. And this is was studied by Contrariani and Thomas in the context of their stable pair theory on surfaces, and the virtual class was constructed later by Kuhl and Thomas using the stable pair theory of Contrariani and Thomas on surfaces. And again, we were happy to see that if you should specialize our virtual class to this information, we cover for invariance. And we also recovered the reduced stable pair invariance of Kuhl and Thomas. So the next inverted scheme is interesting because not only is some new object and well-defined, it also recovers and glues some of the known invariants and some of the known theories from the past. Okay. Now let's call these invariants. So this is the nested invariant, and I'm still in the case that I have two-fold nesting, and I have N1, N2, some curve class, and this is that appropriate cohomology class T1. You don't have me what I call the T1, just because I stole it from my paper. So some cohomology class integrated against this virtual cycle, with the virtual dimension I gave you, is giving us the invariance. Okay. So I talked about construction of these spaces and the virtual cycles and so on, definition of invariance. Now we would like to compute them and hopefully calculate numbers and see if there are any connections between these things and other parts of, some triple geometries or maybe even physics. So for each of calculations, I will again ask theta to be equal to 0. So this is the nested invertible of points, but the number of points could have large gaps in theta. Not this one. So this is highly singular, and it has a virtual cycle. And the virtual dimension is N1 plus N2. Okay? Alright, so this is the nested invertible of points, and my notation is f of N1 bigger than N2, and why is that? Because if you want I1 sits inside I2, and these are functions vanishing on N1, many points on N2, any point N1 should be bigger than N2, obviously. Okay, so as I mentioned, the nested inverted scheme sits inside the ambient product of inverse schemes. So this is sub-scheme inside here, and the reason that this simplifies the calculations is that these ambient guys are smooth, by what I showed you before. Okay, so we would ideally like to integrate some cohomology class alpha prime or something of appropriate degree, I call it T1, against the virtual cycle in here. And then we were wondering if we could use the ambient to smooth the space to do this calculation. So we thought, what if we have some class of the correct effective dimension, something sitting in the middle cohomology of the ambient space. The dimension of the ambient space is 2 times N1 plus N2. So we were thinking, what if we have some class sitting in the middle cohomology of the ambient space, and we pull it back, restrict it to the virtual locus, and then integrate it? Well, it should give us a number, no? And then we were wondering, can we kind of relate this integral to the integral of that cohomology class sitting in its home, but over there we need to increase the degree by N1 plus N2, because otherwise this doesn't make sense. So of course what needs to fit inside the box needs to be some N1 plus N2 dimensional class. And we were hoping whether these two integrals are equal to each other. So the question mark first question mark in here is what should I put in here? The degree I know, N1 plus N2. And the second one we were hoping if it is equality. So this is some sort of push forward, pull back process for integrals. Okay? So this is the theorem that we proved. If you have non-singular projected surface in some line bundle, I will tell you why I need a line bundle later, and this is that cohomology class alpha, which sits in the middle cohomology theory, cohomology of the product of the ambient and smooth spaces, then subject to the condition that alpha is somehow universally defined for any smooth surface and such line bundle and information of N1 and N2. And again, I tell you what it means to be universally defined for such things. As soon as you see the example, you will see what it means. And subject to the fact that alpha is somewhat well behaved under the degeneration of this underlying surface, and again, this is because it's the proof use of degenerations, then this is the formula. So all you need to focus here in this slide is the blue part. Okay? The integral of the pullback of alpha against the virtual cycle is equal to integral of alpha, which sits in N1 plus N2 part of the cohomology here, and some N1 plus N2 Stern class of some object E N1 N2 we call it. And what is that object? This object is some element of the K group of this product. Its description is this way. It might look complicated, but it's really not. What this thing is, this is the push forward of O of S of N1, S of N2, and S onto the product. So K theoretically speaking, this bracket here means fiber-wise over every point in this product is some tuple I1 and I2. The fiber of this piece on I1, I2 in here is H0 of O minus H1 of O plus H2 of O. It's an alternating sum of the cohomologies of push forward of O. And the fiber of this thing is half I1, I2 minus X1, I1, I2 plus X2, I1, I2 and so on and so forth. So this is basically some sort of universal object in the K theory of the ambient product of inverse schemes which understands the trace-free extensions of I1 and I2. Okay? Because of the construction, this object has rank N1 plus N2, and you can take the Stern class of the K group, and there's no problem with that. And you actually prove that our integral, the missing piece inside that black box, the blue box in my picture, is this cohomology class. Okay? In order to prove this, we assume first that our surface is toric projective. In particular, we assume that our surface is either P2 or P1 times P1. We need toric projective property because we are using toric localization in order to prove the equality of these two left-hand side of this identity. And the reason that we pick these two is that these two surfaces, toric projected surfaces, are generators of the cobordism ring of the smooth projected surface. Okay? So we have the results correct and holding true for the generators of this cobordism ring. then we can use some argument saying that if alpha, this is the second line, behaves well with respect to degenerations, by some algebraic cobordism technique, we can show that if this identity holds true for the generators of the cobordism ring, then it holds true for every element of that cobordism ring. So then we can extend our result from the toric projective surfaces to all non-singular projective surfaces. Okay? And this is something that is known. This kind of technique has been used before by Ihlenfreude, Gautier, Lenz, also Pandey and Levine, it has been used before. So prove it for toric projective surfaces, use some cobordism argument, using degenerations, and then you have it for all elements in that ring. In this picture is about degenerations, I will not cover. Okay, so what is it we have discovered is that integral of the full back of this cohomology class alpha now can be recovered from integral of alpha cut with the n1 plus n2 dimensional cohomology class. Okay? And so then the question is, what should I put for alpha? Any alpha you pick, as long as it satisfies those properties, and as long as it fits in the middle cohomology n1 plus n2, it works. But well, we just thought maybe for the fun of it, we just use alpha to be the same as n1 and 2. And we thought maybe for even adding more fun to it, we twist it a little bit by some line bundle. Now, I should tell you, of course I'm joking, this thing, the way we got into this integral is that we did the problem backwards. We were studying certain down totality variants of certain triple geometry, and we ended up with a local calculation on the surface. And this integral showed up for us. Okay, so we realized we need to study necessary things, and we need to study this particular integral. Okay, so let's just take somewhat twisted version of En1 and 2 for alpha. What does that mean? En1 and 2 was the universal object taking care of all alternating sum of the straight C extensions of I1 and I2. I can twist O by some pullback of some line bundle M on the surface, and I can twist I2 here also by the pullback of some line bundle. Okay, so that's just a twisted version. It's not so far from the previous object. So this is the generating series we computed. If I take this twisted guy for alpha, now remember that this integral here had a something equivalent on the right-hand side, which is this guy. So this is what I wrote in that formula, and it's really this one, so I'm integrating over this ambient product. And so now we can let n1 and n2 vary, as long as we are in the nested locus, so n1 needs to be bigger than n2, and then we need to keep track of n1 and n2. So we keep track of them by formal variables q1 and q2. Okay? And this is what we compute. And in order to get this closed form formula, we use the vertex operator language defined by Carlson and Kunkov. If you remember the integral on the ambient product of infinitesimal points, it's like, to me really, the simplified version of that is that I'm integrating something over s of n1, s of n2, and I'm putting this e thing there, like a function, but I'm putting it twice, so I'm integrating s squared. But one of the s's is actually a twisted version of that, okay? So these, the vertex operator language, actually there is an operator to integral of f, and we just realized that because by looking at our kernel, we just realized that our vertex operator is a twofold composite of the vertex operator of Carlson and Kunkov. So we just needed to learn about the language of vertex operators and how to compose them. And that's what we did when we calculated this generating series. Okay? Now, of course, it's important from the innovative geometric point of view if this thing is modular. It's not. Because of the asymmetry between powers of Q1 and Q2, you can see that this thing is not modular. But it could be modular if Q1 is equal to Q2. Okay? And maybe later at the end of my talk, I can tell you why we expect this phenomenon, why we should expect Q1 to be equal to Q2. So that now brings us to the original motivation to study these nested history screens. We were trying to do some threefold geometry. So local visiting invariants on local threefolds. Imagine our surface again. This is my picture that I have in mind whenever someone tells me local surface threefold. So you have this algebraic surface, and you have some line bundle on it with this condition. So the line bundle times the anti-canonical has sections, and we have some threefold, non-compact threefold, which is given by the total space of this line bundle on the surface. And we would like the surface again to be non-singular projective and this time definitely simply connected. Okay? Now, we would like, the goal is to construct some moduli space of sheaves on this non-compact threefold. So what do we do? On the rational cohomology of the base surface, we can pick Chern character vectors. So on the base surface is still the cohomology runs from H0 to H4, so I can pick some R gamma M sitting inside H0, H1, H4. Okay, so if, for example, imagine if you had a bundle on the surface, its strength would be R, its first Chern class would be gamma, and the second Chern class would be M. That's it. So we pick some Chern character vector on the surface, and then we can construct some moduli space of sheaves E, this pink thing, or red thing, which are supported set theoretically on the base surface. So what are these sheaves? These are compactly supported sheaves with complex two-dimensional support. So these are sheaves realized as modules over the ambient structure sheet of the Bragi. These are OX modules, but they are supported set theoretically on the zero section of this non-compact threefold. Okay? And how do we parameterize them? Of course, when we parameterize things, we need to fix Chern characters, right? The way we parameterize them is that we would like the Chern character of the push forward of the sheet, when you push it forward onto the surface, equal to the given fixed Chern character D. So we call this moduli space of sheaves with Chern character D after being pushed forward, which are supported on this total space of L, and of course we need a notion of stability. It's a hyperbolic class, the surface is projected, so it comes with a polarization, and the object plane class on the surface things to be H, then I can discuss about H stable sheets on the surface. Okay? So these are our sheets. They are not stable, they're not T-series stable in the threefold. They are stable when you push them forward and use the slope of stability on the surface. So this is the particular kind of moduli that you're looking at. Okay, and the picture is really something like this if you like. Okay. So, how do we do invariant theories? You need to integrate on this moduli state, and you realize that even your threefold is non-compact. So your moduli state definitely is non-compact, no matter what cohomology class you integrate. And so you need to do localization. So often, for localization is one of the remedies. So it turns out that there is a torus acting, dilating the fibers of this line bundle L, with respect to which, we can localize the moduli state. So it also induces an action on the moduli state, and so it makes sense to discuss torus fixed locus of the moduli state. And so that thing could be compact. And if it is compact, then there is some obstruction theory, and some torus equivariant obstruction theory, blah, blah, blah. It eventually gives you some virtual fundamental cycle. Okay? And this is a cycle in the child homology of the torus fixed locus of the moduli state, with respect to which, after torus localization, we can integrate. So this is our definition of the reduced Donaldson-Thomas invariant. Reduced here, let me not go into it, because it turns out that somehow this torus fixed part of our obstruction theory has a trivial part, which kind of imposes the virtual class will vanish unless you take it out. So with some manipulation, we reduce the cycle, and Jun Lee and many others in this conference already talked about reduced theories. So this is that kind of reduced theory. You take that trivial piece out. The one with Euler class is zero and gives you no invariant, no non-zero invariant. Okay, so we constructed the reduced theory, and this is basically a Atiyah type localization formula. It's really due to Ponte and Graeber virtual localization. So you have some cohomology class, and you're dividing by the Euler class of the virtual normal bundle, which Ponte and Graeber showed us could be recovered from the moving part of the obstruction theory. Okay, and this defines for you this reduced Donaldson-Thomas invariant. Yeah. So this is a invariant, and now something interesting turns out. So if this line bundle is the canonical bundle of the surface, then an alpha is strictly 1, alpha could be allowed in that case to be equal to 1, then the result of this integral after torus localization becomes equal to also some equivariant constant, so this is some equivariant constant to the minus the arithmetic genus of the surface, becomes equal to Vafa-Witten invariance. So these are solutions to the moduli space of Vafa-Witten equations, and we just realized that our Donaldson-Thomas invariant precisely becomes equal to that. Tanaka and Thomas, as Chris talked in the first talk of this conference mentioned, they also wrote a paper on this. Actually, in fact, I should mention our paper appeared before them, but they were kind enough to let us know that, hey guys, it seems like you're calculating the same thing. And so how is this possible? Because when you look at their moduli space, it's different, their obstruction theory is different, and our invariance just matched. The reason is because both of us use torus localization. The torus fixed part of our obstruction theory, as well as torus fixed part of our moduli space, precisely matches with Tanaka and Thomas. And that's why our invariants are precisely equal. Okay? And they did something else too, which was really cool, which was they had this obstruction theory and they made it self-symmetric. So the virtual dimension of their moduli space was 0, and they could use this latest Euler characteristic formula of computing invariance, this Barron function. The Barron function invariance, though, was not using localization, and the invariance they calculated with Barron function is not the Vafa-Witten invariance. In fact, the only invariance which uses the Vafa-Witten invariance is the one by localization. That's why their invariance is the same as our invariance. Okay. And the Vafa-Witten invariance by the beautiful paper of Kamran and Witten in 1994, they are predicted to have modular properties. Okay? So what is the relation between this threefold geometry and the Nesta-Gilbert scheme? Well, it has to do with looking at the torus fixed locus of this moduli space of torsion sheets. Torsion means dimension of support of the sheet is less than dimension of the Archimedes. How sheets are supported on the surface. So it has to do with looking at the torus fixed locus of this moduli space. The claim is that this guy decomposes into several components who care about several partitionings of that rank R. Remember the Chern character vector with R gamma M? These components care about the partitionings of that rank R. And why is that? Let me show you the analysis in the short time I have, maybe 10 minutes. So remember your non-compact threefold. This is a projective map on the plane surface. You're looking at a torus fixed point in the moduli space. This is given by P star equivariant sheet, and we would like the sheet to be stable. Then what we can do is we can push forward the sheet onto the surface. After all, everything we measured about the sheet, including the Chern character or its stability, is after being pushed forward on the surface. It turns out the push forward decomposes into graded pieces. Okay? So these graded pieces I will call E minus I, or maybe EI if you like. And this thing, what does this say? This map, this affine map, is the fibers of my line bundle, and the C star acts on it. So these graded pieces, this T basically here is some trivial bundle on the base surface who have non-trivial equivariant structures. So it has a C star weight equal to 1 if you like. And this basically keeps track of what weight space this EI sits in. So your push forward of the sheet decomposes into weight spaces E1, E2 all the way of rank lambda 1, lambda 2, as long as the sum of the ranks, of course, needs to be equal to the total rank, which is R. So this is how you get different partitioning. So there are so many different ways of dividing a sheaf of rank R on the base surface into directons based on what you choose for these ranks. Okay? And so where's the nesting coming from? Okay, so this is how. not only you will get the decomposition into weighted spaces, you get something like a Hitchens-type map, or a Higgs map, if you like. So those of you who work with Higgs bundles and so on, you know already about this. There is a co-action by the functions in the vertical direction, which actually gives you a map from here to push forward to E times L. Okay, so, and actually if I started just with this Higgs-type bundle or Hitchens pair, the spectral construction will give me back the torsion sheaf I had on the triple. And the hypothesis story actually is the story of G-sets. So they constructed an obstruction theory for G-sets. They started from the surface. So if you look at the Mathematical equation, actually you can see that there is some bundle on the base surface, some torsion-free sheaf on the base surface, with some homomorphic map which takes values 2, 4. It takes values from in endomorphism algebra in here my fewest lower star of E times canonical. And this is exactly that. The spectral construction gives us the torsion sheaf back. So we started from triples, they also recovered triples, but they did different obstruction theories. Okay, so the next thing comes from the fact that, remember that this L itself carries a weight, C star weight 1. And each one of the I's sits inside the EIT weighted space.